Hi, I am Shant Kumar B. Patil, Professor, Sai Vidya Institute of Technology, Bangalore. I welcome all of you for this video lecture on closure properties of regular expression. All of you know that regular expression is, so it is a expression. Generally, expressions separate the variables or separate the numbers. Is called expression, whereas regular expression separate the symbols in the finite automata. So such a expression we call it as a regular expression. These expressions are closed on the or relate with the special operator called as a the Boolean operator. Such a concept we called it as a the closure properties of regular expression. So under Boolean operation, we have union, intersection, difference, complement. We will see one by one. First, we'll perform union operation. To perform union operations on any two finite automata or any two regular expression, we need to find out the language L1 and L2 of the two machines or two finite automata. Then perform union operations on the two languages L1 and L2 to obtain the language L3. Combine two machines or finite automata to perform union operation. Apply language L3 on combined machines to obtain machine for union operation. We'll follow these steps for the two machines or two finite automata. This is the one finite automata for this language, or you can call it as a the regular expression. For example, if they are separated by the operator, so this is a regular expression. Okay, so these are all regular expression. Regular expression. Or you can take the language. So in order to perform the union operations, we need to find out the regular expression of the this machine or language of the this machine, then the regular expression or language of the this machine. The language accepted by the first machine is, so L1 is equal to, it is accepting 1. It is accepting 0 and 1. It is accepting 1, 1. 1 and 1. It is accepting 1, 0. So it is accepting 0, 1, 0. So it is accepting 0, 1, 1. 0, 1, 1. The language or the regular expression accepted by this finite automata is, so 0 is accepting, 1 0 is also accepting, double 0 is accepting. This is the first 0 and second 0. It is again going to take us to the final state. Hence double 0 is also accepted. 1 double 0 is also accepted. 1, this is the 1 0, second 0. So 1 double 0, 0 1 0 is also accepted. 0 1 0 is also accepted. 1 0 1 0. So this is a 1 0 1. So 0 is also accepted by the given finite automata. So it accept the finite number of the this type of the strings. So it is going to accept the finite number of the strings. To perform the union operations, we need to club these two with the union operation. So after performing the union operations on the two languages or the regular expressions, uh, we concluded that L1 union L2 is equal to, so the string which is existed in the either this language or this language or both the language. So we are recording in the L1 union L2. So L1 union L2 on these two finite automata. So it's a equivalent regular expression or the language is this. So if you are performing the union operations on these regular expression or the language or the finite automata, so we are going to get L1 union L2 is equal to 0, 1, 00. So like that finite. We need to construct the finite automata for this union operation. Hence, we are combining these two finite automata. Okay. So once you combine these two finite automata, we are going to get the new state called as a WY. WY, WZ. So this is the WZ. Then XY. So XY. This is the XY and XZ. Next, we need to mark the transition between all these states. So the states formed is one is W with the Y, WY, WY. Second one is WZ, WZ. So W is multiplied with the Z. Then X is multiplied with the Y. X is multiplied with the Y. Then X is multiplied with the Z. So all these are new state, and in that this will be the initial state, because in the these two finite automata initial state is a WY. Hence the transition you need to mark between all these states on 0 and 1. So begin with the initial states. The new initial state is, it is a WY. What you can do, so construct the tree. W on 0, so W on 0, it is a W. W on 0 is a W. Y on 0 is a Z. It is a WZ. W on 0 is a WZ. So WY on 0 is a WZ. WY on 1. W on 1 is, it is a X. It is a X. Y on 1. Y on 1. Y on 1 is, it is a Y. So WY on 1 is a, it is a XY. WY on 1 is a XY. On 1 to XY. Next, so you need to find out the two branches. One is on 0 and other one is on 1. Okay, so the leaves nodes are different compared to the this one. Hence, if they are different, you need to find out the branches for the this new state. 0, one branch is 0 and the second branch is on 1. W on 0, W on 0 is a W. Z on 0, so Z on 0 is a WZ. So the node, root node and this leaves node, they are same. WZ, so WZ on 0 is a WZ, so it is a come back to the WZ only on 0 to WZ. Next WZ on 1, W on 1 is it is a X, W on 1 is X, Z on 1 is a Y, XY. So this pair is repeating. Hence, for this, there is a no branch, even though it is a repeating. You can construct so two branches for this new pair 0 and 1. WZ on 1 is it is a XY. WZ on 1 is XY. On 1 is XY. XY on 0. X on 0 is X. X on 0 is X. Y on 0 is Z. Y on 0 is Z. XZ. So XZ is again the new pair. XY on 0, it is to the XZ. This is XZ. XY on 0 to XZ. XY on 1. X on 1 is, so it is a X. Y on 1 is, Y on 1 is, it is again Y. Y on 1 is Y. So this pair and this pair is similar. Hence XY on 1 is a loop. XY on 1 is a loop. XY on 1 is loop. This is XY. Okay, XY, this pair is repeating. So no need to construct the branches for this XY. XZ is a new pair, so you need to construct the zeros and ones. Two branches, 0 and 1. X on 0 is X, X on 0 is X, Z on 0 is, it is a Z, XZ. Okay, XZ. XZ on 0 is a loop. XZ on 0 is a, it is a loop. XZ on 1. X on 1 is, X on 1 is X. Z on 1, it is Y, XY. XY. This pair is repeating. This pair is repeating. So this pair is repeating. Hence, construct the, stop the construction of the tree. Mark XZ on 1 is a, XZ on 1 is a XY. XZ on 1 is a XY. XZ on 1 is a XY. Hence, all the pairs are these leaves nodes are repeating. Hence, construction of the, stop the construction of the tree. Okay. Finally, so this is how the figure looks. Combinations of the two machines, the neat one. So this is how the finite automator looks. Okay. Now you can perform the union operations on this machine, L1 union L2. So L1 union L2, the first string is, it is a 0. The first string is 0. So any string begins with the initial state. So Wy on 0 is a, so Wz. So 0 should be accepted. That's what I am making the Wz as a the final state. Now it is this machine is accepting the string which is there in the L1 union L2. So this is the final state. Final state Wz. That's what we are marking Wz as a final state. So you can mark this as a final state. Wz as a final state. It has to accept 1. Okay. So Wz, it also begins with the initial state XY. XY on 1 is, it is a XY. Wi, Y on 1 is XY. Hence, the XY is also a final state. XY is also a final state. I am making XY, Wi on 1, Wi on 1. It is a XY. XY is a final state. It is a final state. W0, double zero. So it has to accept the double zero. String begins with the initial state called as a xy. First 0 to the wz, second 0 to the this wz. Therefore, so already we marked the wz as a final state. Next string is it is a 0 1. So next string is a 0 1. 0 1. So from the initial state wy, 0 to the wz and 1 to the final state called as a xy. It is already marked xy, hence no need to mark one more time. Okay, 1 1. So from the initial state wy and 1 to the xy, xy and 1 to the xy. You can take like this 0 1 0 0 1 0. So you can take 0 1 0. It has to accept even 0 1 0 also. So begin with the initial state called as a xy on 0, it is a wz on 1 to the xy on 0 to the xz. Hence the 0 1 0 is there in the union operation. It has to be accepted by the combined machine. So that's what I'm making the xz as a final state. This is how you can perform union operations on these two given finite automata. And each finite automata is having its own language or the regular expression. So this also finite automata is having the regular expression or the language. See, final figure looks like this. The neat figure wy and 0 wz xy is a final state, xz is also final state in the case of the union operations. Like that, you can perform the intersection operations on the two finite automata. The language accepted by the L1 is this, the language accepted by the L2 is this. If we are performing union operations on this, that is a L1 intersection L2, intersection operations on this, L1 intersection L2, common things. So 1 0 is a common in the both the language or regular expression. 1 0 is recorded in the L1 intersection L2. 1 0 0 is there in this also. 1 0 is a 0 is also accepting. 1 0 0 is also accepting. 1 0 0 is also accepting by the first machine. So here also in the second machine also 1 0 0 is there. You can record 1 0 0. Like that intersection operations on the two regular expression or language. It is this one is the common. So this one is the common. Okay. Now the machine already we combined the two machines. So this is the combined machine M1 and M2. So on this combined machine, we need to perform the intersection operations, which accept the strings which are there in the intersection operation. It has to accept 1 0. So begin with the initial state, that is a xy 1 0. It is to the xz. Hence, I am making xz as a final state. I am making xz as a final state. It has to accept 1 0 0. So from initial state xy and 1 to the wy and 1 to the xy, 1 0 to the xz, next 0 to the xz. Hence 1 0 0 is also accepting. It is going to take to the final state called as xz. That's what I'm marking xz as a double circle or accepting state. 0 1 0. So 0 1 0, again it is taking to the xz. Xz is the final state. So only one state is the final state in the intersection operation, that is a xz. Why xz is a final state? Because in the finite automata 1 and finite automata 2, x and z are the final state. There is a common is there. Similar features are there between the state x and z. That's what xz is the only one final state in the case of the intersection operation. Finally, the intersection, after performing intersection operation, the combined machine looks like this. Only xz has a common features. X and z are final state in the two given DFA. Hence, only the common features in the two machines are, that is a xz. So xz I am making as a final state. Difference. So we are finding the difference between the L1 and L2. Whatever the common is there get cancelled, and the non-common things of the this L1 is recorded in the L1 minus L2. So maybe 1 is there in the L1, you will never find the 1 in the L2. Okay, that's what we recorded 1 in the L1 minus L2. 11 is there in the L1. L2 11 11 is not there. Like that 0 1 0 1 1 1 0 1. So these are all the regular expressions. Difference operations. These are the strings obtained by performing the difference operations on the L1 and L2. Once you get the set of the strings or the regular expressions by performing the difference operation, you can apply this difference operations on the this finite automata. What is the difference between these states of the finite automatas? So here it is a common. Both are initial state. So it is a similarity is there. So if we are comparing this final state with the initial state, there is a difference. There is a difference. Their features are totally different. This is a double circle, and this the finite automata begin with this. The finite automata end with this. There is a single circle, double circle. A lot of difference is there between this pair x y. So that is what I am making the x y. I am finding the difference in the only the state x y. Hence, I am making the xy as a final state. If you are making xy as a final state, so it is going to accept 1 is accepted, double one is also accepted, 1, this is the second one, double one is accepted, even 0 1 1 is also going to accepted by the this finite automata. This is the finite automata which accept the different strings obtained by L1 minus L2. Finally, the figure looks like this. For the difference operation, so this is the figure. It is going to accept the strings like a 1 double 1 0 1 0 1 1 1 0 0 1 0 1. The last operator in the closure property is a complement. So there are some steps are there in the case of the complement. Before designing any finite automata or performing complement operations on the regular expression. So first we need to obtain the epsilon NFA or NFA for the regular expression. Convert the epsilon NFA or NFA to DFA, complement DFA, convert DFA to regular expression. See, I have taken the regular expression 0. So each symbol is a regular expression, and each regular expression is having its own finite automata. So this is the NFA for the regular expression 0. 0 we need to convert this NFA into the DFA, because in the steps we need to convert the NFA into DFA. That's what we are converting this NFA into the DFA. For example, you can take A on 0. So A on 0, it is going to take me to the B. A on 0. A on 1, it is going to take me to the A on 1. There is a no transition. Hence, you can mark the state called as a pi. So this is the new state. B on 0 is a there is a no transition. You can write it as a pi. B on 1, there is a no transition. You can write it as a pi. So pi on 0, it is generally it is a pi only. So pi on 1, it is a pi. In the transitions, pi on 0, it is a pi only. Pi on 1 is also pi. Hence, there are three states are there in the DFA. One is pi, B, and other one is the A. A, B, pi. So A on 0 is a B, A on 0 is a B, A on 1 is a, it is a pi. So if you want, you can mark A on 1 to the pi, or otherwise you can keep, because we do not have the one symbol in this, and that's what we are not considering this part of the tree. This part of the tree we are not considering, because symbol 1 is not there in the given regular expression. Hence only 0 is there. We are considering this A with the 0, B with the 0 only, B with the 0 only. So we are not considering even this part also. We are not considering even this also. Pi on 0, it is a pi only. Pi on 0, it is a pi. Okay. So once you get the tree, A on 0, this is 0. A on 0 is a B. A on 0 is a B. B on 0 is a pi. Pi on 0 is a pi. So complement this DFA. Next step is complement the DFA. So in the case of the complement the DFA, all non-final states becomes the final state, and the direction of the transitions are exactly reverse. So it was A to B, now it is a B to A. So some of the states are the dead state, because from the initial state neither you can reach the pi nor you can reach the B. Hence, these two are the non-reachable states, almost called as a dead states. Dead states are removed before finding the regular expression of the machine. Hence, the final regular expression after eliminating the state called as a B and the pi, so remaining is only A. So regular expression of such a finite automata is, it is a epsilon. Thank you.